Hi everyone, good morning. Thanks for coming. My name is Chen, as he introduced, from Uber, and today I'm going to talk about the hierarchical clustering algorithm using Spark. Okay, so why clustering? Clustering is actually a very basic data mining techniques, which is unsupervised learning for people to reduce data redundancy and also to define the data categories. In particular, often we use hierarchical clustering for its richer representations. Not only can it output the clustering results, but also suggest the structures or the relationships among the clusters. It has been widely used in a variety of applications. So let's take a Uber's example, where it basically divides the cities into a set of hexagons. And to calculate the demand and supply, each hexagon can be as small as 300 meters by 300 meters. For the size of San Francisco, we can have tens of thousands of hexagons. But does these hexagons give drivers any human understandable information? So of course not. If I give the driver a hex ID, like 1, 2, 3, 4, without looking at the app, they wouldn't know where to go in the city. So internally, we actually have the service to aggregate all these hexagons to different levels of clusters. The cluster can be at the neighborhood level or the city level. In this way, it helps us to position our drivers in a more human understandable manner. So we can send them a message, hey, it goes to the Hayes Valley or it goes to Marina, whatever, because currently there's a lot of high demand. Okay, so if we only have one city, tens of thousands of hexagons, life is easy. We can just run this kind of hierarchical clustering algorithms on our laptops, and so far so good. However, we have operations on thousands of cities and millions of hexagons need to be calculated. So this is no longer possible for us to process such amount of data on our laptop. We need to actually resort to much more powerful parallel path frameworks such as Spark to help us crunching this data. In the following talk, I'm going to just show you how we parallelize these hierarchical clustering algorithms using Spark and achieve a linear speedup. So before we actually dive into any technical details, let's just refresh a memory a little bit on hierarchical clustering. There are two kinds of hierarchical clustering. You can go bottom up or top down. So in the agglomerative or bottom up approach, initially we start with each point being its own cluster. At each step, we find two closest clusters and combine them into a single one. We repeat this process until all the data points belong to the same clusters. In a divisive method, all the data points actually started with a single cluster first. We recursively divide them into two clusters and so on and so forth as we go along. In this talk, I'm only focused on the agglomerative approach. In particular, I'm going to only focus on the single-linkage hierarchical clustering. Okay. So single-linkage hierarchical clustering is a very simple one, but it actually is a very good representative for us to work through the procedures. So let's start by defining a measurement, the measurement metric. And here we use Euclidean distance or dissimilarities between the two groups. And we start the algorithm by creating a separate clusters for each data point. So if we have n data points, then we have n clusters in total. We compute the cluster distance scores between all pairs of clusters, and we store and reuse them for efficiencies. When we start, so at each step, we compute and we trying to find the closest distance between the clusters and identify these two closest clusters and merge them. At the end, we save the clustering results and output the sequence of cluster operations. Okay, so initially, each data point, as we said before, is a cluster. Computing the distance between all pairs of data points takes like n square computation time, but on top of that, we need to sort them to find the smallest distance. So the computation time at the beginning is actually, the first step is n squared log n. So let's walk through how we do the merge on clusters. We need actually, as we said before, we need to actually calculate all the possible distance for all pairwise points. And after we find out there's two red dots here, and we're trying to, because that's currently the closest point, and we're trying to merge them. And once we merge them into a new cluster, so the distance need to be computed again. Most distance will stay the same, only the distance between the new clusters to the rest of the clusters need to be recalculated. And on the right side, we also draw these dendrograms to visualize the whole process. So we take these 2 points and then connect it with a line. The height of the line is actually indicates the distance or dissimilarities between these 2 points. So let's go to the next iteration just to have more ideas. And then we select the bottom pairs, which is the second closest pairs in this graph, and merge them and recompute the distance again, the same as the first iteration. And this merge process actually adds n log n computation to our total computation time. And we once we merge these two points on the right side of the dendrogram, we basically are also connecting these 2 dots with a line but much higher distance than the first one. So we repeat the process and until we reach the termination conditions. So the termination conditions can be 2 different types. You can actually have some sort of predefined K clusters. Once you hit the desired number of clusters, you can stop, or you can wait until all the clusters belongs to the same, all the data points belongs to the same cluster, then you can stop. And so just to summarize, the total runtime of this particular algorithm is n squared log n, and the space complexity actually is n squared. The reason is we need to store all the pairwise distance. As you can see, with millions of data points, these algorithms were not going to be feasible for us to compute in a single computer. So in the following, let's actually introduce the parallelized version of this algorithm so that we can actually crunch more data. So the main idea of this talk basically is trying to reduce these hierarchical clustering problems into a graph problems. The very important theoretical findings we use here is the following. Give us data sets to calculate its a single linkage hierarchical clustering dendrogram is actually equivalent to find the minimum spanning trees of a complete weighted graph, and where the vertices are the data points and the edge weights are the distance of any pair of the points. So this is a very important and very interesting. So it helps us to partition the data in a very nice, intuitive way, and also later on you see the slides more, and you can find out that it helps on the load balance, helps on the reduce the inter-process communication as well, so that we can actually achieve like a linear speedup. So the parallel strategies naturally becomes in order to parallelize these algorithms, we need to design the algorithm that can partition large scale complete graph and then merge all these intermediate solutions into final solutions. Okay, so to show you the process of the problem decomposition, I'm start with some toy examples. So in these examples, I have a very, very small data set with only 6 data points. I divide it into 2 disjoint data sets, D1 and D2. And the original graph can be decomposed into 3 graphs. Like the first 2 graphs are completed weighted graph from D1 and D2 respectively. And the third graph basically is a complete bipartite graph formed by the D1 and D2. So this process can be reversible. So if you take the union of these 3 subsets, you can actually return to the original graph. So which means like we don't lose any information here. We keep all the edges and we keep all the vertices. So once we have these subgraphs, then we can distribute all these subgraphs to different processes and then apply the local MST algorithms on each subgraphs, and all these algorithms all these MST calculations can be done independently. That's why we achieve our good parallelism. At the end, how you actually we actually have techniques to merge all these MST together to form a single MST, which is the final solution for the original graph. Okay, so minimum spanning tree. I think everyone knows how to calculate minimum spanning tree. There are like usually two popular algorithms. The first one is classical. Classical basically, you start with all the vertices, and also you need to know all the edges weight. Each vertices start with its own tree, and then you create an edge set as well. So in this edge set, you basically contains the edge weight, and also in order to calculate the minimum edge, like in more efficient way, you basically use priority queues or min heap. So the iterations goes like this. So if the set is not empty or the forest is not spanning enough, then we actually trying to find the smallest edges from this set. And as long as this set connecting two different trees and not creating cycles, then we actually add it back to the forest and remove from a set. So this whole process actually is a E log V, is the number of edges times the log number of vertices, complexities, and the space is the number of edges. So on the other side, for the prim algorithms, because it actually is not, prim algorithm you don't need actually require a full set of edges. You just start with one arbitrary vertices and use the vertices local information to calculate the minimum edges, and then grow these trees one at a time. So these prim algorithms actually have much better time complexities and also the space complexities as well. So in considering this, considering especially it's a very, very efficient on the space complexity, we use prim algorithms for our local MSTs. And remember, in our original decomposition problems, and we have two types of subgraphs. So one is like complete weighted graph, the other one is complete bipartite graph. For the prim algorithm, there's no existing way to calculate the bipartite, so we actually modified a little bit. So in the code, we have two types of prim algorithm to actually calculate MST for two different types of subgraphs. Okay, at the merge algorithms, because we already have all the edges from the prim algorithms, so we basically can use the classical algorithms in this case to pick. So remember, like for the mapper and reducer framework, and we speed out all the key value pairs and aggregate by the key. And in the reducer side, we basically pick the smallest edges from all the prims like edge sets. Then we can select then we can select the edges which hasn't been used and construct the merged MSTs. So this is actually very, very neat techniques. So in order to for us, I mean, it helps us to save the memory pressures, and also on the mapper side, the mapper doesn't need to store it, just emit. And then on the reducer side, you can just very efficiently pick the minimum because it's already incorporated in the program model. Okay. Okay, so there are like so in order to merge the trees more efficiently, we use union find the data structure, and which amortize the log n complexities. And for each like merge iterations, you can actually do k-way merge, and the k is configurable. The reason k is configurable is like if you actually aggregate all the MSTs all at once, it actually is not going to be optimal. The reason is you're going to create a lot of like communication pressures, contentions on one single node, and also if you have a lot of edges, then you are not going to fit in one node. So later on, our experiment shows actually k equal to 2 gives you a good, like a very good running time. The reason is even though you have a much longer iterations, but each iteration is much shorter. So in total, it actually gives you better results. So let's move on. And since we already know how to parallelize the single linkage hierarchical clustering, let's see how we actually integrate with the Spark. Because the Spark is using like a lazy realization, they also provide like very nice APIs. The actual driver code is very lean and very short. And the first part is pre-partition. We basically take data points and trying to partition it into different subgraphs. And then this partition also does like a load balance as well. And the next step is trying to apply prims, local MSTs to each subgraphs. At the end, you have iterations to apply the classical reducers. And these classical reducers can, depending on the number of k, it actually is then you can have different iterations to reach the converge. So for the pre-partitions, as I mentioned before, you divide the data sets into S splits, and these S splits actually end up with the following subsets. The first part is the number of a complete bipattern graph, and the second term is the complete weighted graph. So you tag based on this. Once you have this subgraph, you need to actually tag them into different IDs so that local prim can differentiate which version of the prim algorithm need to be used. And at least you also need to know, like a bipattern graph actually have twice number of vertices as the complete weighted graph. So for the load balance, you basically need to figure out how the one bipattern graph is equivalent to two complete graph, so that you can actually have the CPU balanced. So for the local computation phase, because thanks to the Spark, it only start to realize until we actually issue the reduce by actions. The advantage is that we don't actually need to store the edge set, produce the bioprim results. We can actually emit it as it's generated. So it's very, very like memory like efficient. And then the other thing is when you do a reducer, when you're doing reduce, if the data is already in the same box, it will schedule reduce it at the same box as the mapper generated. So this will actually help to reduce the data shuffle. Okay, so the merge phase, as we mentioned before, it's pretty very configurable, and you just do the mod to the partition. Basically, is just mod operations. Okay, so now let's move on to the performance. So in order to demonstrate this algorithm's performance, we actually evaluate the cluster scalabilities up to 2 million data points with feature dimension like 5 and 10. So algorithms, as the results indicate, it achieves really good like a linear speed up over 300x on around like 400 computer cores. In addition, we're gonna see the performance comparison between the Spark and MapReduce, and see how these two different frameworks actually have such dramatic performance difference. So we actually, for the data sets, we did not use a priority to use our in-house data. We basically use IBM's data generator. And this data generator, you can generate the random data sets, or you can generate the cluster data sets. So we have these two different type of distributions to actually validate our algorithms actually it doesn't matter which distribution it comes from. The reason is we are using Euclidean distance, but if we trying to use different metrics, it might matters for distributions. But for this specific case, we did not see any difference. So that's basically the data sets, and you can also download the generator to generate by yourself. So here is the CPU, the total runtimes comparisons between the Spark and the MapReduce. So without any doubt, the memory-based Spark greatly outperformed the disk-based MapReduce for all the data sets. More importantly, the execution time used Spark decreased much more quickly than the MapReduce. I think the reason probably being the RDD in the memory, which reduces the amount of data to be materialized. And the other thing probably is per each iteration, Spark doesn't need to have the teardown and the spin setup of the instance as in the MapReduce. So the overhead per each iteration also reduces as well. So at this particular graph, we're trying to summarize the speed ups for different along different cores per different data sets. As we expected, if you have the bigger data sets and with a high dimensionalities, actually you achieve a much better speed up. So the black line here is a ideal linear speed up line. And if you see the blue line is 2 million points with 10 dimension feature factors, and you can see it achieved like the best linear speed up. But as we mentioned before, this the random or the cluster distributed data set doesn't make too much difference. They all collide to each other. So okay, so let's move on to the K-way merge. I think the one thing which is a little bit counterintuitive is to think probably like k equal to 4 will give you a very nice performance. However, in this case, you will see like a k equal to 2 actually give you a much better performance than k equal to 4 and k equal to 8. As we discussed before, even though the larger k leads to very few iterations, however, it might introduce a lot of like data shuffle at the first, at the first iterations, and it might not use multiple reducers, leverage multiple reducers. But if you have a much smaller and you have much more reducers, and you can parallelize reduce parts and have a better performance. Now let's look at because if you go to like a Spark UI, you can also actually get the metrics for the bytes read and the writes. So let's just examine the I/O patterns and the communication patterns in context of Spark here. So for the data shuffle patterns in this graph, and the x-axis represents the Spark iterations from 0 to 8, and the y-axis indicates the aggregated amount of bytes remotely read by all the reducers per iterations. As the data sets increase, the required number of splits increase as well, and which means like the number of subgraphs increase, the number of computer nodes increase, which as a result, the number of data bytes shuffled will be increased as well. However, one thing to be noted here, from the first iteration to the second iteration, you will see this line, and it's actually the data reduced very dramatically, like 25%. The reason is like because we merge, we reduce the graph such that they have some overlapped vertices, and this actually reduce a lot of like communication overhead. So by playing this trick. So at the end, let's just to give a very, very high level of how this algorithm actually implement among all the clusters. On the left upper corner, you will see this is the CPU, the utilization heap map. It actually tells you how your load balance actually behaves, and you will see like because our algorithm actually incurs very little communication overhead, so this communication part is actually pretty green, and the whole algorithm actually is heavily lifted by the prim algorithm. So the CPU cycles actually is pretty heavy. So this whole algorithm is CPU bound rather than a communication bound, which actually explains why it achieve linear speed up. So at the first iterations, you will see like all the data shuffles almost the same color, and at the end it will reduce to smaller reducers, and only a few computer nodes are active. So in here, this graph shows you the later iterations, and the first graph shows you the first iterations, and the orange means like the bytes. There's more bytes like shuffling in those iterations, and here, since you already passed the by couple iterations, and then the number of bytes actually communicated through per iterations actually reduced dramatically. So this actually helps you to understand the whole algorithms along the runtime. Okay, to conclude this paper, we actually have two takeaways. So the magic part is basically trying to to reduce the original clustering problems into graph problems. It actually helps you to visualize the problem better and to partition the problem into subproblems much more intuitively and much more like intelligently. So the other thing is we use classical reducers, which actually have a very small communication overhead, and allows us to achieve the linear speed up. So I can take any questions.
Excellent. We should have time for one question here. Anybody looking to, anybody with a question here? Here we go.
It looks like when you code use RDDs.
Yeah.
How hard would it be to change that to using data frames? Not very hard, right? You just
Probably not. Probably straightforward, because this one written like 2 years ago. I think it's Spark 1.0 or something. So as long as they support like a backward compatibility, it should be straightforward.
Very cool. Thank you.
And we do have another 30 seconds for another question if anybody has one. All right, thank you very much, Jen. This was an excellent presentation.